friends, we are here to discuss about a wonderful topic called limit fits and tolerances. We are here to discuss about the limit fits and tolerances, which is a very important topic from the metrology. Now, what is metrology? Metrology is nothing but it is the measurement, it is a science of measurement. Okay. Now, why do we need a different department or different subject altogether to measure something? If I want to measure this pen, can't I simply take a ruler and measure it? Yes, of course we can do that, but will it be accurate? That is a bigger question here. So, will it be accurate? It will not be accurate. There are more chances that that result will not be the true value, right? So, the measured value differs from the true value. And why does it differ? Because it basically differs because of three things. Let us talk about two laws that I want to tell you first before we discuss anything further. The first law says that you cannot measure anything accurately. If I want, suppose this is a shaft of, let's say, 100 mm length, right? Will I be able to manufacture a shaft of that length exactly? The answer is no. You can only manufacture somewhere near to that 100 mm. That length could be 99.9 mm or it could be 101.9 mm or something like that, isn't it? But there are very, very small chances that you will be able to manufacture it accurately. Right? Second point. Second point says, even though I manufactured it accurately, there is no such system that is so accurate that can let me know that this length is actually 100 mm. Because of these two laws, what we have to do is we have to accept that there are going to be inaccuracies, there are going to be imperfections, there are going to be certain deviations from the true value, and that is why we have to come up with some solution. And what is the solution? Metrology or limit fits and tolerances will give you the solution to that. Okay. So basically what I mean to say is that any production process involves three elements. Now what are these three elements? Element number one, let me show it on the board. It's man, then material and machine. Okay, man, material and machine. So whatever you see around yourself, and if that is man-made, just remember those things have been actually that involves these three elements. Let us start with the machine. What is machine? What is a machine? Machine is nothing but it is a integral unit of small components. Now let us go back to the first law. What first law said? That you cannot manufacture anything accurately. Fine, I accept that. But sir, our machine is an integral unit of small components, and those small components also have been manufactured somewhere else, and they have been brought together, they have been assembled, and you have got a machine. Fine. So does that mean that because a machine has been actually made up of small components that are actually inaccurate by themselves, so when they are integrated together, they won't be able to manufacture something accurately? Yes, exactly. This is what I mean, right? So machine cannot manufacture anything accurately. So it can help you to manufacture somewhere near the desired value, but not the exact desired value. You can never achieve that, right? Now let us come to the material. Let me give you the example of a very simple example so that you can understand. Let us take a coin in our hand. You have a certain body temperature, and because of this temperature, what will happen? A certain amount of heat you are going to give to the coin. Its temperature is also going to rise, and depending upon its coefficient of thermal expansion, it is going to expand. Now this expansion is going to be there. Whether this expansion is small, it is large, or it is negligible, it is up to the material how it wants to behave depending upon its own thermal properties. But you cannot deny this fact that there is going to be a certain expansion. Now, even if there is a small amount of expansion is going to be there, what is going to happen? The measured value is going to deviate from the true value. So that means here also you failed to measure the true value of the diameter of that coin. Got the point? So we have completed machine and material. Now let us talk about man. Now man is the most unpredictable element of the production process. Why he is so unpredictable? Because man has got many attributes and that varies every single day. Let us take the example of an engineer or an artisan. He is performing some turning operation on lathe machine, right? And one day he was very happy. So he very excitedly and he was very committed towards his job, and he performed excellently. The second day, his mood was not so good. His mental status, that means we are talking about the mental status, is different this time, and his performance got affected because of that. So suppose he got replaced with some other person. Now this person has a different amount of skill set. His experience is going to vary. The first person had 15 years of experience on the same machine. Now this guy has only 10 years of experience in the same machine, on the same machine. Skill set are going to vary. So actually this is just a small thing that I am sharing with you, that mental situation, the skill set, the physical condition, the physical situation also hampers the productivity, and it also affects your performance. That you cannot deny. It happens with you also, right? Very good. So I hope that you have understood that all these three conditions, and because of all these three elements that are the essence of any production process, these three things actually cause inaccuracies, and you cannot avoid these things, right? And that is why the inaccuracies are always going to be there. Fine. Now I understood this thing. Now sir, if there are inaccuracies, then how can we manufacture something accurately? Now for that, what we have to do is, we have to develop some kind of understanding between the designers and between the manufacturers, right? So we are going to talk about that now. So I hope that you have understood so far completely, and I'm going to jot down some points here. I am going to write it down because there are so many things to write today, and then we'll see. Okay? Alright friends, have a look here. So on the board we have mentioned the exact same thing we have already discussed. So let us go through all these points one by one. The first point says it is impossible to manufacture any part precisely to a given dimension. It is impossible to manufacture any part precisely to a given dimension. Even if by chance the part is made exact, it is impossible to measure it accurately to prove it. If attempts are made to achieve perfect size, the cost of production will increase tremendously. Therefore, some permissible variations in the dimensions have to be allowed. So after this, that we have understood that why the deviations occur, now we are going to step into the concept of limit fits and tolerances, and we are going to learn about the same. Alright friends, have a look here. So after discussing about the deviations, the first point that you need to learn is the limits. Now what are the limits? Limit means what we are going to do, say this was the shaft that we wanted to manufacture. Its length was 100 mm. So instead of giving the manufacturer, when we are giving the design to the manufacturer, we are going to provide some relaxation to him, right? Because we know that he's a good and talented manufacturer. There is no doubt in his abilities, even though because of all these laws, there will be certain variations. So what we are going to do is we are going to provide certain, we'll say that, okay, if you can't manufacture it exactly 100 mm size, it is okay even if it lies between 99 mm to 101 mm, 99 to 101 mm. So that means you are getting a relaxation of 2 mm, I think, which would be easier for you to manufacture within this limit. Then he is going to agree because of that, because he has got a certain relaxation. Getting the point? Yes. So the 99, which is the minimum limit, is known as, of course it is the minimum limit, and 101 is known as the maximum limit. As you can see that the size or the dimension is made to lie between two limits, maximum and minimum. It's a relaxation, right? Now similarly, there is another term called tolerance that we need to talk about now. This is tolerance. Now what is tolerance? Tolerance means the difference between maximum limit and the minimum limit. Getting the point? So this relaxation that we are talking about, that the manufacturer has got the relaxation of 2 mm, right? So this 2 mm is nothing but the tolerance, that we are going to tolerate this much of deviation. Getting the point? So it is nothing but only the relaxation or the dimension deviation that you can tolerate. Alright friends, let us have a look at the definition of the tolerance. The permissible variation in size or dimension is called tolerance. Also, the difference between maximum and minimum limit is known as tolerance zone. Okay, so if within this zone the size of the component is going to lie, then it will be said to be accepted, right? And if it crosses the minimum or the maximum mark, it is rejected. Got the point? Yes. So that's all about the tolerance. Let us move further. Alright friends. So now, after learning about limits and the tolerance, let us talk about the systems of writing tolerance, how you can provide the tolerance. The first system is unilateral. Unilateral means there is some basic size. Basic size means it is the size, it is the nominal size actually that you desire, and if you want to show the maximum limit and the minimum limit, it has to be shown with respect to the basic size. Okay, so the dimension of a part is allowed to vary only on one side of the basic size in unilateral tolerance system or unilateral system. So you can see the examples: 25 plus 0.02 plus 0.00 mm. So the basic size is the minimum limit itself, and 25 plus 0.02 is your upper limit. Similarly, you can see here it is on the negative side. So here in this case the size is getting bigger than the basic size. Here it is getting smaller than the basic size, and over here again it is getting bigger than the basic size, but they are actually getting bigger only. It is not like the dimension is going to come down from the basic size, or it is even lower than the basic size. So no, it is not like that. So the minimum limit is the basic size itself, over here and over here. I hope that you have got the point. This is known as unilateral tolerance, and in a similar manner there is another system called bilateral tolerance. So here I have not mentioned the definition because it is already understood. So let us see the example: 25 plus 0.02 and minus 0.02 mm. It can even grow bigger than the basic size. It can become smaller than the basic size, but the dimension has to lie between these two limits. Getting the point? I hope you have got the point of unilateral and bilateral system. Now let us move to the next point. Alright friends, after learning about the limits, the tolerances and the systems of writing tolerance, now it's the time to discuss about the different terminologies, and let me tell you that there are n number of terminologies associated to the limit, fits and tolerances. So before we start writing or before we start solving the numerical problems, we have to go through all these theoretical part and all these terminologies, and these terminologies are very simple to understand. There is nothing complicated at all. Okay, so firstly what we are going to witness is a diagrams of this kind, and by now you would have recognized that this diagram is about a shaft and a hole. Right, now where is a hole? This hole, this dimension, this outer, the bigger rectangle that you can see, it's the front view of the hole, let's say like that. And there is a shaft which is actually smaller in diameter with respect to the hole, because a shaft goes inside a hole, and it in any assembly it happens like that only. Like even let us take the example of this marker and this cap. Let's say this is the shaft and this is a hole, and it will go inside and it will get placed like this on, and this is how we have got an assembly, right? In a similar manner, all the assemblies are assembled, or in the similar manner. So what we are going to determine is, so this is your hole and this is the shaft, and you can see that there is something blue shaded area. Now can you tell me what this shaded area means? This shaded area is nothing but the tolerance zone. Okay, so just now we have determined that you provide the limits to everything that you manufacture, whether it is hole, whether it is a shaft. So in a similar manner, hole has got two limits. The hole could be as big as this size from here till here, and it could be as small as this size from here till here. And also, hole could be of any size between this size, this dimension till this dimension. It can lie between any region within the shaded area. Getting the point? Yeah. In a similar manner, the shaft could be as big as this dimension from here till here. It could be as small as this size from here till here, or it can also lie between. It can have any size between this dimension and any point over here in the shaded area. I hope that you have got the point, right? Okay, so this is nothing but the tolerance zone. Now we are going to talk about certain terminologies. As you can see here, the shaft. So here, wherever we refer shaft as not the actual shaft always. Actually, shaft not only refers to the diameter of a circular shaft, but also to any external dimension of a component. It is not necessary that we are going to assemble shafts only every time. Okay, assembly could be of anything. So it does not only refer to the diameter of a circular shaft, but also to any external dimension of a component. In a similar manner, hole not only refers to the diameter of the hole, actually hole, but also refers to any internal dimension of any component. I hope by now you are getting the point, right? Now basic size, as we have already discussed, what is basic size? Basic size is a size with which, it is a size with which, the reference of which you determine the limits. It is the standard size, as the definition says, it is the standard size of a part with reference to which the limits of variation of size are determined, right? And there is another thing called actual size. Now what is this actual size? Actual size means it is the dimension as measured on the manufactured part. And now also you understand that there will be a difference between actual size and the basic size, right? Let us move to few more terminologies. There are many terminologies actually we have to see. So let us buck up. Alright friends. Now the next point that I want to tell you is your zero line. Now what is zero line? A straight line drawn to represent the basic size, right? Now could you indicate zero line on this diagram? Yes, absolutely. This is your zero line over here. So this line that runs from here between the sizes of shaft and the hole, this is the zero line. and the basic size, it represents the basic size. So that means this size is going to be your basic size. This is your basic size. Alright. Similarly, there is another term called deviation. Now what is deviation? It is the algebraic difference between the actual size and the basic size. Fair enough. Now there are two kinds of deviations, upper deviation and the lower deviation. Upper deviation means the algebraic difference between maximum limit of size and corresponding basic size. Let us read it once again. The algebraic difference between maximum limit of size and corresponding basic size. So if I have to talk about, if I have to determine the upper deviation for whole, so this is whole and the maximum limit of size. So whole could be as big as this dimension, right? And the difference between these two is nothing but this is your upper deviation. Okay, so this is your upper deviation. In a similar manner, if you have to talk about the lower deviation, now what is lower deviation? Lower deviation is nothing but the algebraic difference between minimum limit of size and the corresponding basic size. Now this has been left up to you because you can easily follow this thing, that it is the algebraic difference between minimum limit. For lower deviation, it should be minimum limit of size and corresponding basic size. That means for whole, the minimum limit is what? Minimum limit is this thing. There is a little lesser space, so I am extending this line over here. I hope that you can follow. So this line, you can see that here, this line is nothing but your lower deviation. Getting the point? So this is your lower deviation. Right. In a similar manner, you can determine both of these deviations for shaft. So the shaft could be as big as this size, right? So the upper deviation will be over here. It is going to be this smaller region. So this is your upper deviation for shaft. In a similar manner, for lower deviation means lower size and the basic size. So this over here is the lower deviation for shaft. So lower deviation for shaft, lower deviation for hole, upper deviation for shaft and upper deviation for hole. So we have understood the concept of deviation also, right? Let us move to the next very important term called fundamental deviation. Alright, my friends. Now let us proceed to a very important topic called fundamental deviation. Let us firstly, learn the definition for the fundamental deviation. What is that? It is one of that two deviations, either upper or lower, which is the nearest to the zero line for either hole or shaft. So fundamental deviation is for both hole and shaft. It's nothing like only for hole or only for shaft. It's not like that. And it is one of those two deviations which is the smallest. So if I have to say what is the fundamental deviation for hole, you are going to say the lower deviation. What is the fundamental deviation for shaft? You can see it is the upper deviation. Sometimes fundamental deviation are zero also, depending upon which kind of system you are going to opt for, whether it is a hole-based system or a shaft-based system. Okay, we are going to learn about that later. But as of now, this is fundamental deviation. So fundamental deviation is nothing but it is the smallest deviation in an assembly. Okay, whether it is lower deviation or upper deviation. I hope that you have understood. And when you have to designate the fundamental deviation for hole, it has to be designated using these capital letters. Okay, just remember always that for hole, fundamental deviation is designated using the capital letters. And it starts with A, B, C, and it goes on, and it ends at ZA, ZB, and ZC. I'm going to show you one slide, and where all these fundamental deviations have been arranged and they have been designated, and what are the letters that are used to designate those fundamental deviations. We are going to talk about that. Okay, right. In a similar manner, for shaft, the same thing can be designated by using small letters. Okay, just like the whole, here we are going to use the small letters, not the capital letters, right? And so in totality, there are how many fundamental deviations? There are 25 fundamental deviations, okay? Starting from ABC till ZA, ZB, ZC, right? So these are the codes. Don't worry, we are going to talk about that. We are going to talk about that again in the later sessions. And the tolerance grade. Now, what is the tolerance grade? It is an indication of the degree of accuracy of manufacture and is designated by IT followed by a number, where IT stands for International Tolerance Grade. Okay, so let us learn once again. It is an indication of degree of accuracy of manufacture and is designated by IT. Now, how do you actually show it on the figure? If I have to tell you through this figure, where is the tolerance zone or the tolerance grade? You can see that this strip, right? I have shown this strip to be little thinner as compared to this one. That means the tolerance grade for the hole is smaller than that of the shaft. Let me give you a wonderful example for that. Suppose when you make projects in your final year, you go to a manufacturer. Suppose he is it's a very big company, and it takes very sophisticated orders also from the NASA and ISRO and DRDO organizations like that. Also give order to that manufacturer, and also you went over there and you asked them to manufacture a shaft. You are speaking to the engineer, sir, could you please manufacture a shaft of let's say diameter 50 mm. 50 mm is the diameter of your shaft. He said that, okay, fine, so I can manufacture this thing, but the price is going to be, let's say, 5,000. So you said, sir, 5,000 actually is very less for us because we have a huge budget, right? 5,000 is nothing for a shaft. Fine, we can do that. Now he said that because it is a college project, so you will not be actually very specific about the dimensions, are you? You said, no sir, it's a college project simply. So even if you make it like 45 mm, we are fine by that also. Even if you make it like 55 mm, we are fine by that also. Although I have taken a huge amount of deviation, usually such deviations are not allowed, but since I'm explaining, I'm taking that liberty. Okay, so that means you have got the deviation for 10 mm. You can see it's a huge deviation, right? And because of which he said that earlier I was charging 5,000. I thought that you required a very sophisticated or a very accurate shaft. Now I can, because you're saying you are not specific about the dimension, I can produce that for 3,000. So you were very happy and you came back. Now what happened just after you came back? Another order approached him, and this time this order was from, say, ISRO. Okay, ISRO or DRDO approached this guy, and what they said that, sir, again we want you to make a shaft, and its diameter is going to be 50 mm, but there are certain challenges for you. Actually, we want it to be really accurate. So we are planning is that it is not going to differ much. If you cannot manufacture 50 exactly, which is our required dimension, will be okay with 49.8 mm and 50.2 mm like this, right? So 49.8 mm till 50.2 mm is okay with us. Getting the point? So what is happening here is this shaft that he is going to prepare, he is going to manufacture for an organization such as ISRO, where they are very specific about the dimension, its price is going to increase. But for you people, because you were, it was a college project, it was just 3,000 rupees. The idea behind this explanation is that this tolerance zone can be bigger like this. Okay, you can also show it or indicate like this. It can grow bigger like this. Okay. Also, it can become very small, very, very small. So what does it mean when it is bigger, when it is wider? That means you have got a huge amount of tolerance. That means it is some kind of your college project. And when it is very, very narrow, very thin, that means they are really, really specific about the dimensions. And that is why the prices are going to change, are going to vary. So this is what we understand from this statement, that it is an indication of degree of accuracy of manufacture. If it is narrow, accuracy is more and is designated by IT followed by a number. Okay, we are going to talk about this thing later. But as of now, I hope that you have understood the concept of fundamental deviation and the tolerance grade. Let us move to the next point. Alright my friends, let us have a look at the next point, which is also very important, called fit. Now what is a fit? It can be defined as it is the degree of tightness or looseness between two mating parts. So suppose an assembly, you will find that some assemblies are very easy to assemble because there is a lot of room for those two mating parts to adjust, right? And some are really, really tight because there is a very small amount of room. Sometimes you have to push, you have to apply a lot of effort in placing those assemblies, right? So it is nothing, a fit is nothing but it is a degree of tightness or looseness. Okay, so let us take an example of, let us take the example of this marker here once again. So you can see that this marker goes inside this cap very easily, but till we hear a click, we know that it is not yet done. Okay, so that means what we have to do is we have to apply small amount of force like this, and now it's done. I hope that you can also hear the click, right? So this click actually signifies that it is a tight fit. You have to force this marker to go inside the cap and be secure there like this. So actually this creates an airtight seal, isn't it? So that means this is a tight fit. Which kind of fit? It is a tight fit, and tight fit actually resembles interference fit. Now let us talk about all the fits from the beginning. Clearance fit. Clearance fit means the shaft size is always going to be smaller than the hole. Okay. Now, which you may ask that, sir, shaft is going to vary, right? Its size is going to vary. Even in your example, in your figure, the size of the shaft is going to vary. You can see that this is the shaft. This is the upper limit of the shaft, and this is the lower limit of the shaft. So which size actually you're talking about? I say it's a very nice question. Actually, the size, the shaft, the maximum size of the shaft. If you want to take this shaft, this size of the shaft, so be it. Even this size of the shaft is going to be smaller than the minimum size of the hole. Okay, so you can see this is the minimum size of the hole, and when you place them together, you will always find a clearance between them. Okay, so this kind of fit is known as clearance fit, where the shaft is always going to be smaller than the hole. Doesn't matter which limit actually you're talking about. Right? I hope that you have followed the clearance fit. Now let us move to the interference fit. Interference fit means the minimum permissible diameter of the shaft. Just mark my words here, that the minimum permissible diameter of the shaft is bigger than the maximum allowable diameter of the hole. That means the shaft is going to be the smallest possible shaft that you can think of in one particular assembly. That shaft is also actually larger than the maximum allowable diameter of the hole. Getting the point? That means for this, let me tell you, let me draw one figure for that. So usually what we do is we take this zero line, okay, here we draw a zero line like this, and we represent the hole like this. Okay, I am considering a hole basis system. For those who don't know what hole basis system is, do not worry, we are going to cover that soon. But as of now, it is a hole basis system, just accept that fact. Now, shaft. So that means the hole, suppose this is 50 mm size, this is the basic size, it has been indicated by using the zero line, and the minimum size of the hole is 50 mm itself, and the upper limit, say it is 50.5 mm. That means this is the tolerance grade or tolerance zone of 0.5 mm, right? So that means the hole can vary by 0.5 mm like this, and the shaft is going to lie somewhere over here. Okay, if you're talking about the shaft, it is going to lie somewhere over here, because the lowest possible size of the shaft is also even greater than, just a minute. So suppose this was the upper limit of the shaft, right? Now let us see, this is the lowest limit for the shaft. That means there is a gap, there is an overlap. Okay, so this kind of fit will result into interference fit, where you have to actually force the shaft to move into the hole and reside. Getting the point? Yes. So this is nothing but the interference fit, or it is also known as tight fit. The best example that I can give you, and you have also observed that example, is your lunch boxes and the tiffin boxes. Yeah? You must have heard of Tupperware, and this is a company that produces all these airtight containers, right? Especially tiffin boxes and water bottles like that. So they are actually famous for creating airtight containers. And how do they manage? How do they manage to create airtight containers? It is all about the fit, the degree of tightness or looseness. So the fits will be, you must have observed that placing the cap over container in case of Tupperware containers, it's not an easy task. Okay, you have to apply a certain amount of effort to do that. Okay, because the caps are made little smaller than the size of the container. So that is why they are able to hold it properly, and they create an interference fit. Getting the point? Where the shaft is bigger, or the hole, the exterior dimension of the container is bigger, whereas the cap is actually smaller. So you have to stretch it, and it is a stretchable material by a certain amount, and that is why it holds and it becomes airtight. I hope that you have followed my example. Now let us move to the next point. It is known as transition fit. Now what is a transition fit? It lies midway between interference and clearance fit. So what happens is that for the same hole and shaft assembly, you are going to obtain clearance fit sometimes, you are going to obtain sometimes the interference fit. Now how it is possible? I want you to think over it. It's a point to ponder. Okay. So what you have to do is you have to think that when this case is possible, sometimes you are going to obtain an interference fit, sometimes you are going to obtain an clearance fit. Let me give you a hint that actually this whole magic lies between the tolerances. Okay. Where these tolerances lie actually. And because I told you that the hole could lie between any size, between these dimensions. Okay, it could be like this, like over here. It can have any n number of dimensions between these two limits. Similarly, the same thing goes for the shaft. Now what you have to do is you have to think of such a system where these limits coincide. Okay. Now I have given you enough hint. I want you to think about it and do it yourself. Okay, a small home assignment for you. Now let us move to the next statement. Alright friends, let us move to the next important point called allowance. Let us define it first. It is the clearance or interference which gives the tightest possible fit between two meeting parts. Okay, let us read it once again. It is the clearance or the interference which gives the tightest possible fit between two meeting parts. So anything, any clearance or any interference that gives the tightest possible fit is known as the allowance. Okay, if you are not able to follow it for the first time, read it once again, and I'm going to anyways give you an example. We are going to solve an example that will showcase the allowance. Okay, and yes, so it is the clearance or interference which gives the tightest possible fit between two meeting parts. Now let us talk about the systems of obtaining different types of fits. Right, we have just now covered an important point called fits, and now we are going to learn about this different systems of obtaining different types of fits. Okay, so first system is hole basis system. Now what is hole basis system? Let me tell you that. So the hole basis system utilizes this fact that firstly, a hole will be created and the shaft dimension will be determined on the basis of the hole dimension. After learning about the hole basis system, let us talk about the shaft basis system. It is of a similar kind. The only difference over here is that the shaft dimension will be determined first, and then the hole dimension will be determined. Okay, now which one you are going to prefer? We as an engineers, we prefer the hole basis system. Why? Because it is easier for us to firstly drill a hole and design a shaft based upon that dimension. Because in the shaft basis system, what will happen? The shaft will already be there, and then to make a hole of that dimension where the shaft can reside securely, you need a long process actually. Firstly, if you're literally talking about a hole in the shaft, then for that hole you need to make a manufactured drill bit, custom made only for that shaft, which is going to incur a lot of money and effort and time also, right? So that is why, to reduce our effort, time and money, we go for hole basis system. It is generally more preferred. Getting the point? Yeah. So that's all about hole basis system and shaft basis system. Now let us move to the next point. Alright. So now we are going to discuss about the designation, which is a very important topic. It is just like, it's like the heart of this topic, of this chapter, limit, fits and tolerances. So what happens is that whenever you create an assembly, you designate that assembly in some manner. Okay, so you designate in some in this way. Now what is this 50 over here? Let me tell you, this 50 is the basic size. 50 indicates the basic size, right? So we'll do one thing. We'll keep on jotting the points also. So 50 over here is nothing but your basic size. Now we learned that somewhere we learned, if you can remember, if you can recall, that something for a hole is represented with the capital letters. And what was that? That was the fundamental deviation, if you can think of. Now fundamental deviation is the nearest deviation, whether it is upper deviation or lower deviation for a hole or a shaft. Getting the point? Yes. So H, I think H is designated using, H is actually, H indicates the fundamental deviation, right? Yes, so H indicates the fundamental deviation, and you have already learned that it is designated using the capital letters. So this is the fundamental deviation, but for what? For hole, because it is capital letters. So fundamental deviation for holes. And what is this 7 here? This 7, actually I have not told you about this thing, so let me tell you directly that 7 indicates the tolerance grade. Okay, because you must remember that in the definition of the tolerance grade, we saw that IT, I mean the tolerance grade is represented using IT followed by a number, if you can recall. So what is that number? That number is nothing but this 7. Now the only thing is that we are not representing IT in the designation. We are not representing IT7 in the designation, but actually it stands for that itself. Okay, just be patient. We are going to cover the entire thing very systematically. So this is your tolerance grade. Tolerance grade. Now for what? Of course it is for holes. It is for hole only, because 7 is associated with H, right? In a similar manner, you can see this F over here, and by now you can understand fundamental deviation. It is a fundamental deviation, but for what? It is for the shaft, because it is represented in small letters. Very good. So this is the fundamental deviation for shafts. This is for the shafts. And what is this 8 stand for? Again, 8 represents IT8 actually. It represents IT8, and since we are actually talking about the designation, that is why we don't have IT mentioned over here, but actually it stands for the same thing, IT8. Now I will be telling you about the importance of IT8 and IT7. Just let us finish this part. So this is tolerance grade again, but for what? For shafts. Very good. So this is your designation part. I hope it is very clear to you, right? Now, I want you to have a look on your screens. Okay, we are firstly talking about the fundamental deviation. You can see that the fundamental deviation has been represented for both the hole and the shaft on the screen. Have a look. So the pink or the red blocks actually are nothing but these are the tolerance grade. We are considering the same tolerance grade as of now, but this tolerance grade could be very small till very big. Getting the point? At every particular point, this is possible. This is true, right? So we are going to consider, say, we are going to start from the A block, which is on the extreme left in red color, and actually it indicates for what? Fundamental deviation for hole, because it is in capital letters. Now you can see that the lower limit, you must see that there is a small block like this, right? So the fundamental deviation is this limit, right? So the fundamental deviation for A is actually very high. It is very high, right? In a similar manner, for B it is lesser, C is even lesser, CD, D, E, EF, and so on and so forth. You can see that it goes down also, right? Starting from A till ZC, it declines. The fundamental deviation is declining. Now, there is one special case for whole basis system. What was that? And what is that? That when it is coming down, it is declining like this. You can see that at one particular point, you can see that the fundamental deviation becomes 0. And what was that? What is that actually? That fundamental deviation is, what is the code name? It is H. Okay. So whenever you see H mentioned anywhere, you are talking about the fundamental deviation which is 0. And for whom? For shafts. Because it has been represented in capital letters. I hope that it is clear. Now in a similar manner, let us observe for the shafts. Now the fundamental deviation for shaft has been represented on the right hand side in blue color. You can see it starts from the bottom and then it grows up. We are following the exact same thing, but the direction and the representation is different. They are represented in small letters. So A, B, C, then C, D, D, E, exactly the same thing. Till ZC it is going on, right? Now it is climbing up. Now you can see also there is a special case. And what is that special case? It is that the fundamental deviation for shaft becomes 0 at one particular point while climbing up, right? Now what is that? You can see that the fundamental deviation for the shaft becomes 0 for one special case. And what is that? It is small h. It is small h, right? Yeah. So for these two special cases, the fundamental deviations are 0. Very good. That means how many fundamental deviations are there? There are 25 types of fundamental deviations. If you want, you can count them from A to ZC. There are 25 fundamental deviations. I hope it is clear. And how it has been represented, it is also clear. Now, let us talk about the tolerance grade. Okay, the tolerance grade. Right. The tolerance grade is actually given by, it starts from IT01, IT0, right? Yeah, IT0 and IT01, IT02, IT03, 04, 05, 06, 07, 08, or no, just a minute. I made a small mistake. Sorry. It is there will be no zeros over here now. Okay. So after IT0, it will be IT1, 2, 3, 4, 5, 6, 7, 8. Similarly, okay, 9, then 10, 11, 12, 13, 14, 15, and 16. And everywhere it is IT, like this, okay? IT7, IT8, IT9. Fine. Now these are just the codes, okay? These are just the codes. They contain some meaning, right? So, but for that you have to deduce the meanings. Now what happens is that when you're talking about the accuracy, these IT grades are actually so fine that we do not use it for general purpose, okay? So let us not talk about these IT grades, because these IT grades are very fine. They are very small. That means when you move upwards till IT01, your accuracy is actually increasing. Okay. Now what happens is, let us talk about IT5 onwards. All right. So IT5 has some value, and what is that value? Let me indicate that with a different ink. It is 7i. Then it is 10i for IT6, then it is for IT7 it is 16i, for IT8 it is 25i, and then 40i, then for 10 it is 64i, and for 11 it is 100i, for 12 it is 160i, for 13 it is 250i, for 14 it is 400i, for 15 it's 640i, and for 16 it is 1000i. Got the point? Now what is actually happening here is, let me tell you. See, I, what is I? Firstly, let us talk about I. Let us define what is I. I is nothing but I is a constant. Okay. Now what is but it must be having some name, right? Yes. So I has a name, and it stands for, I stands for standard tolerance unit. Okay. What? I stands for standard tolerance unit. I am going to mention it over here. Will it be visible? Yes, of course. So I is nothing but standard tolerance unit, right? Now I has to be actually computed. I has to be computed. Now how you are going to compute I? I is just one number which is in microns. Okay, it is a dimension. It is a length, you can say. Okay, and it is computed using this formula: 0.45 cube root of d to the power 1 by 3 plus 0.001 times d. 0.001 times d. So this is how you are going to compute the standard tolerance unit, I. But for doing that, what you have to do is you have to determine this d. Now what is this d? Do not be mistaken, d is not the diameter of the shaft or hole. Let me tell you. Okay, it is not the diameter of hole or the shaft. Actually, d is nothing but it is the geometric mean of diameter step. Now, what does it mean? Let me repeat once again. D is the geometric mean of diameter step. Now, how do you calculate the geometric mean? It is under root of some constant A times some constant B, right? Or when I am talking about the diameter step, let me show you the diameter step, and let me indicate the diameter step using, let's say diameter step is D1 and D2. Okay, so what will be D over here? D will be under root of D1 times D2. Getting the point? I hope that you are following. So D is nothing but the diameter step. Now what is a diameter step? Let me tell you. So what happens is that there are certain organizations that have grouped certain diameters, because let me tell you that this I, standard tolerance unit, is in microns. Okay, although you are going to put this value for D over here in mm, I is going to be already in microns. The unit conversion has already been taken care over here. You don't have to convert it into microns and put, no. Directly put it in mm and you will get in microns. That means I has a very small value, right? And if you find the I for each and every diameter, suppose for 50 it is going to be something else, for 51 it is going to be something else, 52, 53, 54, I'm talking about mm's, okay? I'm talking about diameter of the shaft. So if there is a diameter, there is a shaft of diameter 50 mm and 51, then 52, 52, 53, 54, so on and so forth. That means for each and every shaft, for with only 1 mm difference, you are going to obtain n number of values for I. I mean, for every shaft there is going to be one specific value for I. But you will realize that that difference between two I's is not much because it is in microns, right? So what we have done is we have grouped certain diameters that for a diameter of, let me tell you the range also, let's say from 1 mm till 3 mm diameter, the value for I has to be same, okay? So what we do is we take the same value for I between 1 and 3 mm. So this is the diameter step. Between 1 and 3, then 3 and 6, then 6 and 10, then 10, 14, 14, 18, 18, 24. These all are in mm. These are the diameters that we are talking about, right? And these diameters have been grouped. Why? Because we wanted you clearly understand, right? So there is no need of repeating the same thing again and again. So these diameters have been specified by IS 919 here, and we use these two diameter steps to determine the geometric mean, which is D, and we put this value over here in this formula to obtain I in microns. Getting the point? Yeah. So this is nothing but I. So once you have got the value for I, and it is a constant of course, right? So you are going to put that value over here. Suppose I is say 5 microns. That means for IT5 it is going to be 7I. That means it is 7 into 5 microns, it will be 35 microns. Similarly over here 50 microns, right? 16 into I, 25 into I, 40 into I, so on and so forth. That means you will see that for IT16 the size of the window is going to be huge. It is going to be very high as compared to 7I. So usually you will find that we deal with the values between 7I to 16I and 25I also. So you will be using a lot of IT5s and IT8s, okay, between these four things. And over here it is actually very inaccurate product you are going to get if you are following IT16. So that is why we don't usually use this. You will find the maximum use of IT5 and 6, 7 and 8 like that. Okay. So I hope that you have followed the designation and the fundamental deviation and the tolerance grade, and we will try to solve few numericals based on the same concept, right? Let us move to the numerical problems, right? Alright friends, so after that we have covered all the basic terminologies regarding limit, fits and tolerances. Now it's time to use that theory in solving few numericals. And these numerical problems that I'm giving you, they are quite prominent in the GATE examination. And by doing these kind of problems, these are just the kind of examples I'm showing it to you. And you need to practice of the similar kind of questions, and I hope that it is going to help you a lot in the GATE examination if you practice the similar kind of questions from limit, fits and tolerances, right? Okay, so let us proceed. So let us talk about the first problem. And in first problem, I have the datas with me regarding the upper limit and the lower limit for hole and shaft, both of them. And you need to find out few things. Let us see what are the things we need to find out. We have to find out the value of allowance. Okay, so I'm going to write down first what we have to find. Allowances has to be found out, and the hole tolerance and the shaft tolerance, both of them we have to find out, right? So tolerances for hole and the shaft for both of them. Now, what is the dimension for hole? The hole dimensions go like this. The upper limit is 37.52 mm and the lower limit is 37.50 mm. Similarly, for shaft, we have again two dimensions, and what are they? They are 37.47 and 37.40. This is 45 mm. Right. Now we have to find out the hole tolerance first and shaft tolerance, and then we will see the allowances. So what we do is, before solving such kind of problems, we have to draw the figure. Okay. Now the figure would look something like this. Now see, can you tell me what is going to be the basic size here? You can see it is 37 over here and 37. So let us see the base. Let us say the basic size is 37 mm, right? So this is 37 mm, and 37.50 to 37.52. This is the hole tolerance. Yeah. So the bracket or the window would look something like this. So the hole has a lower limit of 37.50. It will be little higher than this, 0.5 mm higher from the zero line, and it will be 37.52 mm over here. Similarly, for shaft, you can see the shaft also has the lower limit and upper limit above the basic size, right? Above the zero line. Right. So you can see 37.47. We'll do one thing. To make some space here, I am going to draw the zero line over here. Okay. It is just a representation. So 37.47, 37.45, they both lie below 37.50. So we have to indicate it like this. So this is for the hole and this is for the shaft, 37.47 and 37.45. Yeah. Now the shaft tolerance and the hole tolerance. You can see it is 37.52 minus 37.50. So that means it is 0.02 mm. So this is the width of this window is going to be 0.02 mm. Right? And similarly for shaft also, you can see the tolerance for the shaft is 37.47 minus 37.45 mm. That means again it is 0.02 mm. So the hole tolerance and the shaft tolerance both are same, which is 0.02 mm. Like this. So in this manner you can determine the hole and shaft tolerance, and using this diagram. This diagram is very important because it gives you an idea like whether the fit is going to be a clearance fit or the interference fit. So would you be able to answer if I ask you which kind of fit this kind of situation is going to give you? So you can see that the minimum hole size is 37.5 and the maximum size of shaft is 37.47, which is still lesser than the minimum size of the hole. That means in any case there will be a clearance of 0.03 mm, right? So this is clearly a clearance fit. Getting the point? Now let us move to the allowance. Now what is allowance? From the definition, you must have seen that the allowance is something, whether it is clearance fit or an interference fit, or we can say that the allowance is a positive allowance or the negative allowance, but it should provide the tightest fit possible, right? So here you can see that what is the tightest possible fit in which, yeah, you can see the tightest possible fit you are going to get only when you have the hole of 37.5 and the shaft of 37.47. That means the least size, the smallest size of the hole and the maximum size of the shaft will give you the tightest fit, the minimum clearance it is going to give you, right? So yeah, so you can see that 37.50 minus 37.47 is going to give you the tightest possible fit, which is 0.03 mm. So which is nothing but the allowance, right? So as we discussed earlier when we were discussing about the allowance, that it will give you the tightest possible fit. So in this way, my friends, we have to solve this kind of problem. This was a very, very basic and very easy problem, just to give you an idea, give you the feel. I'm solving it over here. Okay. Now we will move to the next problem, which is a little tricky, and you will get an idea how to solve that kind of problem, and which is very prominent in the GATE exam also. Right? So let us proceed further. Alright, my friends, have a look here. This is the second problem that we are going to solve, and I'm not giving you any description about this problem, because all these things mentioned on the board is what you require, right? So the first thing that is given to you is the designation of the assembly, right? And as we have learned in the theoretical part, that designation is given like this: 60 F7. Okay, so firstly let us recall it once again, that 60 stands for the basic size. 60 stands for the basic size. H is nothing but the fundamental deviation for what? It is for the hole. Why? Because it is indicated in capital letters. And 8 stands for IT8. And what is IT8? It is nothing but the tolerance grade, and it corresponds to a certain value, right? You have that value in your notebooks. It is 25I. And what is F? F is again the fundamental deviation for what? It is for the shaft, because small letters. And what is 7? 7 again, it is the tolerance grade for what? For whom? For shaft, right? IT7. And again, it corresponds to a certain value that you have to see on your notebook, right? And D1 and D2 have been mentioned. Now, what are D1 and D2? D1 and D2 are nothing but these are the diametrical steps, as we have learned in the previous, in the theoretical session, that we have grouped certain diameters for which we have a single standard tolerance unit, I, right? So these are the diametrical steps, and D that you see in your standard tolerance unit formula is nothing but the geometric mean of these two diametrical steps. Okay, see, these diametrical steps are going to change depending upon the basic size. So this basic size 60 lies in the range of 50 to 80. Had it been somewhere around like 90 or something, so you are going to select the next category or the next group of diametrical steps of diameters, for which you will be having just one single value of standard tolerance unit. Let us now solve for the what you have to do over here. You have to find out the limits of holes and the shaft, right? And the fundamental deviation has also been given to you. Now, fundamental deviation is nothing but it is the nearest possible value from nearest possible distance from the zero line, and it could be for hole also, it could be for shaft also, but for whom this fundamental deviation is given to you, there are two ways to recognize this thing. Okay, the first way is to have a look at the sign over here. If it is negative, that means it is for, most probably it is for shaft. Okay, it is going to be for shaft. In the usual cases, it is going to be like that only. And there is one more thing, that observe the designation. Whether it is a hole basis system or a shaft basis system, you are going to get to know. Since H is the special case where fundamental deviation is 0, that means it is a hole basis system. Hole doesn't have any fundamental deviation over here. F, as you can see, if you can imagine, if you make a mental picture in your in your brain, the figure that I showed you, you start from A, B, C, D, E, F like that. So H is the special case, and below this F is going to lie, right? That means we have yet not crossed the zero line. Getting the point? That means your tolerance window for the shaft is going to lie below the zero line. Getting the point? And what is the distance between zero line and the upper limit of the shaft? That is nothing but the fundamental deviation. I hope you are getting my explanation, right? So let us proceed further. The first thing I do always that I draw the diagrams, because it helps me in visualizing. 60 is the basic size, this is the hole, and for shaft is like this. And yet I don't know these limits, okay? The only thing I know is the lower limit of hole is 60 because fundamental deviation is 0. Okay, now what we have to do is we have to find out the limits. So for that I am going to use IT8, okay? Now this IT8 corresponds to a certain value. What is that? IT8 corresponds to 25I. 25I. Now what is I? I is, as you know, it's 0.45 and cube root of D plus 0.001 D, right? Am I correct? It is 0.45 cube root of D plus 0.001 into D. Now what is D here? See, let us determine D. Firstly, it is the geometric mean, and 80 into 50 and under root of this product is the geometric mean of this thing. So I get the geometric mean as 63.24 mm. So I'm going to put the same value here. And also remember one thing, the unit of I is in microns, although you are going to put the value for D in mm. It is, the unit conversion has already been taken care over here. Okay, so you don't need to convert it into microns. I is 0.45 and 63.24 cube root 0.001 times 63.24. So after solving this, you should get a value of 1.856 microns. Or simply you can mention 0.001 856 mm. Okay, 0.001856 mm. That's all. Now what to do? Let us put this value over here to determine the window, the length of the window for hole. It's 25 times 0.001856. So IT8 you are going to get as okay, so 25 yeah. So I get 0.046 mm, right? So this is IT8. That means this is the tolerance window, 0.0464. That means what about the upper limit for the hole? It is, yes, it is 60.0464 mm. Like this, right? And for the shaft, in a similar manner, you can determine for shaft, it is IT7, which corresponds to a value of 16I, right? Yeah. And by performing the exactly same thing, just multiply 16 into this thing, you are going to get 0.0297. It is 0.0297 mm. Just try it, you are going to get the same value. That means the window for shaft is 0.0297 mm. Fine. Now the thing is that I cannot determine the upper limit and lower limit for the shaft until unless I know this distance from the zero line. So for that, I have one more information, which is fundamental deviation, which is in negative direction. That means it is below the zero line. Yeah. So we have to determine this fundamental deviation over here. So fundamental deviation will be given to you minus 5.5. And what is D? Again, you are going to take this D, not the basic size. Okay. So 63.24. and to the power 0.41. Okay, so let us see what is the fundamental deviation. It will be negative. It is minus 30.11 microns. If we forget about the negative sign because it only tells you about the direction, we can use the fundamental deviation as 0.03 mm, right? It will be 0.03 mm. So this is your fundamental deviation. That means this distance is 0.03 mm. Now we can determine, yes. So 60 minus 0.03, it will be 59.969. Just a minute, I did some mistake, I guess. Yes, 59.97, yes. So it will be 59.97. Let me use a different ink for this. It will be 59.97. And similarly, the lower limit is going to be 59.97 plus, or you can simply add this up, 0.03 plus 0.0297. and 60 minus this thing. So you are going to get 59.94. Okay, so you will get 59.94 mm. So these are the sizes of the shaft, right? So what I have got, that the hole has two dimensions, which is 60.0464 mm and 60.00 mm. And shaft has got two dimensions, 59.97 mm and 59.94 mm. And this is what had to be found out, right? So my friends, you have seen just how to use this formula for standard tolerance unit formula, this one, right? And how to find out the geometric mean and how to use it, and how to convert the units for solving for the fundamental deviation. IT8, IT7 corresponds to certain value and what that value signifies, right? So you have understood completely everything related to the limit, fits and tolerances. Yes. So I hope that you have followed everything so far, and if you want more clarity over limit, fits and tolerances, try solving these kind of problems more. You are going to get a very good clarity, right? So that's all for today. Thank you.